Hello, everyone. Thank you so much for joining us for the first in WBUR CitySpace's Town Hall series on the science, the rollout, and safety of the coronavirus vaccine. We are streaming live from the WBUR CitySpace YouTube channel, and if you haven't already, we encourage you to subscribe so we can notify you whenever we go live, like we are right now. I'm Amory Sivertson.
And I'm Ben Brock Johnson, and we are the co-hosts of Endless Thread, a podcast from WBUR that explores untold histories, unsolved mysteries, and other interesting stories from the internet. And we were asked to be involved in this series of events because of a series that we made back in 2019 called Infectious: The Strange Past and Surprising Present of Vaccines and Anti-Vaxxers.
We're going to be the ones kicking off each of the 4 events in this series by providing some context on vaccines as a whole. So there are so many questions swirling around right now about the COVID vaccine, and we thought it might be helpful to lay a framework for how other vaccine rollouts were managed. And perhaps more importantly, in this event, we're going to try to answer some of the seemingly simple but actually really big questions, like what even is a vaccine? And what is the history of vaccine usage?
And because we're radio people, how do you spell vaccine? After we are done, we're going to hand the virtual mic over to Angus Chen. He's CommonHealth reporter here at WBUR. We know you'll have a lot of questions too, so feel free to start sending those over to us by going to slido.com and using the event code vaccines. And we'll try to get to as many of those questions and get them answered as we can later in the event. That's slido.com. So let's get started.
Great. So first, we should be clear that we, Ben and I, are not doctors. We're not healthcare professionals. We are podcasters, and we are just lucky enough that sometimes we get to talk to doctors and other experts who help us and the people who listen to us all the time on their phones.
Subscribe to Endless Thread wherever you get your podcasts.
Yeah, to help those people understand things that are complex. And about 2 years ago, we were trying to understand something ourselves that was pretty complex.
Yes, and that complex thing was what was looking like a pretty concerning set of outbreaks of a disease that we all thought had been basically eradicated, the measles. If you remember any news stories from the before times, ancient history we know, you might remember that there were a couple of places where in the beginning of 2019, the measles was becoming a problem. Maybe you remember some of this.
Washington State has declared a public health emergency there.
New York State is facing its worst outbreak in decades.
The World Health Organization cites hesitancy to vaccinate as one of the top 10 threats to our health.
It's very hard to change people's minds, especially when you're talking about the health of their children.
So where did these dummies get these dumb ideas? The same place that wants you to believe your miserable aunt and closeted uncle are actually happy. The internet.
So that tape we collected back in 2019, almost 2 years later, it's eerily relevant, right? I mean, without knowing what that was referring to, that tape, you could pretty easily assume that some of those comments were about the coronavirus pandemic that we're all living through right now.
And part of the whole point of our series, which was about the strange past and surprising present of vaccines and anti-vaxxers, is that we have seen the stories of right now before. There have been pandemics, high-speed, high-stakes races to innovate technologies and treatments to fight disease and pandemics, and reactions to medical breakthroughs and innovations. In a nutshell, much as we hate to say it sometimes, history repeats itself.
So as we said, we're sure that you have a ton of questions right now. Just reminder, slido.com. The code is vaccines. That's SLIDO.com, code vaccines. And we're going to get to those questions. We promise we will. But for right now, if you will indulge your Endless Thread podcast hosts for a few minutes, we're going to try to have some fun. Remember fun?
Nope, don't remember fun.
It's hard to come by these days, but we'd like to try.
We also want to give you some historical context for the time that we are in. And we're going to start that historical context where we have often started episodes of our show Endless Thread, which is a post on the internet. A post on the website Reddit, which if you have been paying attention to stock market news over the last few weeks, you might have heard about Reddit. That is a whole other explainer. We're not going to do that tonight.
So this particular post that we're talking about on Reddit was made in something called the Today I Learned community by a user who goes by KPM squared.
The post was about how in ancient China, people used to blow scabs up each other's noses to avoid getting smallpox, which sounds pretty desperate.
We are talking about desperate times, maybe a desperate era.
What do you think this desperate era was like, Amory?
Well, when we first started working on infectious, I really had no idea. So I did the thing you do. Then I Googled smallpox.
Big mistake.
Yep. And I saw things that really you can't unsee. If you've never seen smallpox, it kind of looks like your skin has been turned into bubble wrap. You see people with thousands and thousands of these tiny, painful looking pustules, and it looks and sounds like a nightmare.
I think it was a nightmare, and you don't really have to take our word for it.
There used to be a time when we got infectious diseases and there was nothing we could do other than just kind of live through them or die.
This is Renee.
Hola, soy el Dr. René Nájera y soy el editor del sitio web The History of Vaccines.
Just making sure you're paying attention. Renee Nájera is an epidemiologist and the editor of The History of Vaccines, a website studying the global history of vaccination. He knows a ton about the story of terrible diseases and how humanity has figured out ways to fight them. But also, Renee is kind of our Rufus, the guy who guides Bill and Ted, or in this case, Ben and Amory, on their time travel adventure.
So let's start in the Gobi Desert. Sandy wind is blowing. There's weird rock formations. The sun's beating down on two people. One of them is alive, maybe like wrapped up in a bunch of handmade clothing, and the other person is a corpse. A corpse who is about to do something awesome.
Really, they do it together. It's an exchange, if you will.
Oh, they will. This is how Renee thinks this incredible exchange happened.
My personal guess is that somebody died of smallpox out in the middle of the Gobi Desert. Somebody came upon their body, and the body was desiccated, and they breathed in the dust from the body. And then that person went into some place where there was massive amounts of smallpox. They didn't get sick. And they themselves said, I wonder if it was because I was somehow protected by the spirit, the dust, the whatever came off of that body who had smallpox.
I thought you were going to say that they ate them because they were in the desert and desperate for food. And
that is actually the plot of my next zombie novel. So please don't ruin it.
Okay, so this is just a guess. So this scene is a fictitious one. But what we do know is that any discovery of something that might help fight off smallpox in 10th century China was huge. This was a disease of biblical proportions. And over the course of human history, smallpox has killed about 500 million people.
When it came around, and it did every few years, sometimes through trade routes, smallpox could infect 60% of a population. And a third of those people might straight up die.
So in our reporting, we called up another person who's an expert on smallpox, specifically. His name is Gareth Williams. He's a professor emeritus of medicine at the University of Bristol in the UK. And he wrote a book called The Angel of Death, the story of smallpox.
When smallpox broke out, there was widespread panic. And 90% of its victims were kids under the age of 5. So it had a great reputation as being the slayer of innocence. And if you got it and you lived, you weren't necessarily that lucky, because about a third of the survivors were badly scarred, and they could be hideously disfigured. There are plenty of cases on record of people who survived smallpox and then killed themselves because they couldn't bear to look in the mirror.
So Ben, in our original series, this is where we said something like, we have literally never seen something like this in our lifetimes. But that isn't the case anymore, obviously. We have a much better sense now of the lengths to which people will go to avoid a deadly disease.
True, it is wild to think that we made something not that long ago where we were like, pandemics, a thing of the past. But now it's actually easier to imagine that in the time of smallpox, this person in the Gobi Desert who maybe inhaled by accident some dead guy pixie dust and lived to tell the tale through a smallpox outbreak might lead other people to say, we got to get us some dead guy pixie dust.
Which led to the ancient Chinese practice of drying out smallpox scabs, grinding them up, and blowing them up each other's noses with straws to protect people from the horrible specter of smallpox.
Amory, are you cool if I just blow some old scabs up your nose to protect you from smallpox? I got a straw right here somewhere.
Oh, it's going to be a no from me, dog.
Fine. Nonetheless, this is one form of something called variolation, an early way to make people immune to disease. And China appears to have been one of the very first places humans started doing this. This is a very important piece of our story.
For reasons we're about to tell you.
Back to the time machine so we can skip over a bunch of stuff. The rise of the West.
The Dark Ages, lots of wars.
Couple of plagues.
Bring out your dead!
The Renaissance, Leonardo, Mona Lisa.
Not bad. The quote-unquote New World with lots more war.
Also, more smallpox, which did a ton of damage to indigenous populations in the Americas.
And we arrive in the 1700s in England.
Ben, my time traveling buddy. Are you cool to stay time traveling for another minute here?
I mean, we just did like about 1,000 years in less than a minute, so I could use a snack.
Does milk count as a snack? If so, allow me to bring us now to the end of the 1700s, to a field in the English countryside populated by a physician named Edward Jenner and a bunch of beautiful milkmaids.
You had me at milk.
Oh, good. Okay. Well, here's Renee Nahara again. He says that Jenner, who, by the way, would go on to become a huge name in the scientific community for this, Jenner notices something about these milkmaids. These milkmaids supposedly had it going on.
He noticed that they were pretty. And he notes this in his notes, you know, these fair maidens whose face is not at all reflective of ever having smallpox because it left you with some disfigurations. And he's kind of like, what is all that about? So he gets inquisitive. And he notices that they all get this disease from the cows called cowpox. But it's not bad at all. It's, you know, maybe a fever, maybe a little bit of a rash on the arms and the hands where they've been touching the cows. But that's it. And so he does a quick survey. You know, he becomes an epidemiologist right there. And he says, okay, did you have cowpox? Yes. Did you have smallpox? No. And he goes down the line. And everybody who had cowpox did not develop smallpox. Light bulb moment, right?
Next, Jenner does what any logical person would do. Find and convince a vulnerable test subject to participate in a secret medical experiment.
And so he hires a young boy by the name of James Phipps. And he says, you know, to the father of the boy and to the boy, he says, hey, I'm going to give James the cowpox pus. And then get this, I'm going to expose him to actual smallpox and see what happens.
Oh, man,
And
lucky James.
Yeah, he did not. There was no institutional review board. There was no ethics panel to look in on this. And he does it. And he keeps it a secret, by the way, because if he kills James, he's done for. So he gives James the cowpox with a lancet in his hand. He gives James smallpox, and nothing happens, meaning that it totally neutralized the smallpox. And so Dr. Jenner is like, whoa, I'm onto something here. He immediately writes a letter to other medical friends, to the medical society in Britain. Of course, they were a little bit horrified that he did it, but on the other hand, they were like, whoa, what are you talking about? So they decide to do more experiments like this, and every experiment after that is successful.
Boom shaka. Science 10, smallpox 0, game over, right?
Well, yeah, about that. Dr. Jenner's idea of sticking cow diseases into humans got just a little, like a smidge of pushback.
Just a little. And you know what? Look, I get it. And if you were to blow your nose into a handkerchief and come up to me and try to wipe that handkerchief on me, I would not only be thoroughly grossed out, I would be mad. And having seen what smallpox looks like and knowing what it did to communities, if someone came to me back then and said, I'm going to stick some of that disease in you to try to protect you from that disease, I'd say, hell no.
And if they said, no, 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 it's fine. It's like that disease, but it's actually just a cow disease. How does that make it better? This is a very, very weird idea, at least back then. So maybe not shocking that it got some weird response.
If you look up at some of the cartoons at the time, they had people turning into cows as warnings of what could happen if you got Jenner's cowpox vaccine. No evidence of anybody turning into a cow, but people claim that these things happen. I compare a lot to people who see UFOs. They claim that they saw a UFO, and I wasn't there. I saw a person turn into a cow. Well, how does that work? Well, you weren't there.
Luckily, the proof was in the pudding, which in this case was people actually getting the vaccine and realizing, hey, this is way better than getting smallpox.
And vaccine, the word vaccine comes from the Latin word for cow, vaca. And so that's how we get vaccine.
Oh my gosh. I took Latin and I did not make that connection.
Yeah.
So clearly this is just a quick snapshot of the early history of vaccines. Thank you for letting us come share this little bit of historical context. We appreciate you being patient. And also remember to subscribe to Endless Thread wherever you get your podcasts to hear our series Infectious and the rest of our episodes.
And now that we have arrived at the present, we'd like to present the present with help from CommonHealth reporter Angus Chen, who's going to take it from here. Angus, all you.
Thanks so much, Ben and Amory. Hello, everyone. I'm Angus Chen. I cover health, medicine, and science for WBUR. So it's been 200 years since people were inoculated with cowpox. Thanks for that great history, Ben and Amory. But science and medicine has come a really long way since then. And everything we've learned over the last 2 centuries has gone into the vaccines we've made for COVID. And we're going to talk a bit about these vaccines, how they're different from what came before, the speed at which they've been developed, and some of the implications they have for the future of medicine. So to do that, we've invited Dr. Galit Alter to join us tonight. Dr. Galit Alter is a professor of medicine at Harvard Medical School and a group leader at the Reagan Institute of MGH, Mass General Hospital, MIT, and Harvard. Galit, I hope I said that right. Is it the Reagan Institute or the RAG? Yes? Okay, great.
Just like the ex-president.
Okay, great. Okay, and of course, we want you, the audience, to be part of this conversation. Like Ben and Amory said, feel free to keep sending us your questions at slido.com using the event code vaccines. And Dr. Alter and I will try to get as many as possible. If you have any questions about what you heard in the first segment, feel free to ask Amory, who will be following along in the YouTube chat. So one thing that's changed in the last couple 100 years, Galit, is we actually know what's happening when vaccines get to work. They all sort of have the same, I guess, fundamentals behind them, including the COVID ones. So I was hoping you could give us maybe a quick overview of what exactly an inoculation is.
Yeah, so we've learned a lot about how the immune system works, and we've learned what it takes to essentially make the immune system fight diseases. And so I think the big game changer for us was the discovery of antibodies and how they are raised by vaccination, and how raising the right quality of those antibodies is absolutely key to making outstanding vaccines against pathogens. So with that discovery, what we began to realize is that if we could generate different types of vaccines, improve our vaccines, make the process of vaccine development smoother, control the quality, and ensure that they induce really strong immune responses in all populations, not just in kids or young adults, but even in the elderly, then we can essentially cover immunity against pathogens at a global level. So that was the big breakthrough, Angus, for us, is when we learned how the immune system works, so we can now engineer it through vaccination to make it fight disease.
Yeah. So I heard a scientist talking about the new COVID vaccines. He said that in order to get to the point where we are, it's like multiple Nobel Prizes stacked on top of each other. Like that's the work that's kind of gone into this. And it's, I mean, I guess I kind of want to ask you about some of the technology that's at play here. But I mean, now we have 2 and almost 3 vaccines if the Johnson & Johnson one gets approved, maybe as early as next week or the week after, and they've been brought to clinic in under a year. Normally this process takes it can take a decade. So I guess what happened? I mean, how is it possible that we've been able to accelerate this process as we've done?
So it's really interesting, Angus. It's a really important point. So what has happened is that we do stand on the shoulders of giants, right? Over 2 centuries now, we have learned how vaccines essentially instruct the immune system. And over the years, we have learned what are the stimuli that are required to drive those kinds of immune responses. So progressively over 200 years, we have developed better tools that can train the immune system to make these particular antibodies. We started off, as we heard just in the last few minutes, with using the actual pathogen to try to drive immunity against our pathogen of interest. But then we quickly learned that we don't have to actually use a pathogen and risk the possibility of exposing the immune system to a potential lethal disease. So we began to learn how we could use chemistry and biology to essentially synthesize components of our particular pathogens of interest that could then selectively drive immunity just to those pieces of our target pathogen of interest. The technologies just got better and better. We got more cost effective, we got faster, and more importantly, we also learned exactly the flavors of vaccines that the immune system seemed to respond to most effectively. And so what I mean by flavors is instead of using, a protein, which, we often think of as like, a chunk of steak or a chicken, right? They're made from these molecules, right? That are really important. That is protein. Well, proteins also, these molecules that are coming from the virus are also made from these same strings of molecules that we can actually synthesize through chemical processes. So we were able to make this with our technologies getting better and better, making them at higher quality. But then what we realized is that those technologies to make proteins sometimes still take an awful long time. And the amount of quality control required to make sure that every single protein is folded absolutely perfectly just took too long. It would take us a year just to make sure that, those particular vaccines looked perfect and induced the perfect immune responses. And that's when we began to think about 20 or 30 years ago about the possibility of, instead of trying to make these particular portions of our pathogens in a dish, what if we could tell the immune system itself to make those particular parts of the virus? So now what we have are these enormously fantastic technologies like the mRNA vaccines and the viral vectors that form the basis of the J&J vaccine that essentially just provide the software to the immune system. It just provides the code to make these particular portions of our pathogens, only make that one tiny little part of the pathogen without taking the risk of exposing the immune system to the whole virus itself. But now the immune system makes that protein in our bodies and trains us in real time to respond to it. That discovery has blown apart the vaccine field essentially, because now we can make these faster, we can make them stably, we can make them with incredible high quality, and we let the immune system make these components of the virus naturally and expose us only at minimal risk to the component of the virus that we want to attack.
Yeah, I mean, that sounds so amazing. I mean, essentially, like we were for a while we were trying to make like these pieces of viruses or bacteria ourselves, but I guess we're not so good at that as humans, but our cells are kind of already experts at making biological materials, right? So these new vaccines, the Moderna and the Pfizer vaccines that have this modified mRNA technology, they're they're tapping into the biology of our own bodies in a way, right?
That's exactly right. I mean, I wouldn't say that we're not good at making the proteins. I think we're awfully good at it. I think there are a lot of vaccine companies that have been doing an amazing job at making proteins for, flu vaccination and other vaccines. The problem is that it's laborious and it's slow, particularly for a novel pathogen. What we tapped into here was the ability to essentially use our own bodies to make these particular molecules, which is an enormous leap of time that we saved ourselves, right? And that's what makes this particular technology so very exciting. I think that there's still going to be a need for those protein-based vaccines in the future for other types of indications. But what is critically clear here is that this mRNA approach, or the vectored approach, where we deliver just that software code to tell the immune system how to make those proteins, gives us a leap over those months where we would have been waiting, right? And we needed it in the context of a pandemic. We just could not sit back and wait for those proteins to come on board. Although there are some promising protein vaccines coming up in the pipeline that promise to also be outstandingly effective at limiting COVID-19.
Yeah. Well, so this modified mRNA technology that you've described, since you say it just provides a software to our bodies to make a piece of the coronavirus, does having this technology at our disposal kind of change the outlook when it comes to looking at different variants of the coronavirus or even future pandemics?
Yeah, so the one thing that is really important about these mRNA technologies is their speed, right? So the important thing to remember is that if a variant comes along or a new pandemic comes along, we have speed on our side with these particular technologies. What we're trying to do right now is investigate whether or not the current vaccines are inducing antibodies that can essentially fight all the current variants that are emerging across the globe. And I think the data are promising, and I think the data look like the mRNA vaccines are inducing antibodies that can provide some level of protection against the variants. But should a variant come along, right, which is more complicated for the immune system to see, then we can rapidly design new vaccines that can come in and boost our existing response, but now tweak the immune response to respond now slightly a little differently to these new modifications in the virus, empowering us very rapidly with immunity to fight these novel viruses. So it's all about speed. It's all about flexibility. We have now proven definitively that these platforms are enormously effective. We had no idea that we were going to hit 95% efficacy. That was something that I think all of us were shocked by. And so the question now is, how do we use this new set of tools, these new tools, to begin to really start to tackle pathogens before they even have a chance to begin to grip any given population?
Yeah, that's a really interesting idea. But on the topic of the speed, I mean, you're sort of describing the speed as something that is coming out of the technology, this vaccine technology we have today. And I think that, people were worried maybe early on in the process that the approval process for these vaccines was getting rushed, especially because you kept hearing politicians say things like we would have the vaccine by a certain date or the coronavirus would just disappear by a certain time period. Looking at the science around the safety and efficacy of these vaccines, are there any concerns that we might have cut corners, or is the science really solid here? And the fact that the sort of the speed of its development is something more about the technology rather than maybe a political will to push something through?
That's a really important question. And I think this is a really critical message to try to share with the public. And so I guess So when I think of a definition of a scientist, or I imagine what you would draw in a dictionary or in an encyclopedia when we used to have those, I would think of kind of a nerdy person with glasses and a lab coat, kind of looking over a dish, really with the adjectives I would use would be careful, methodical, and maybe even slow. So scientists by definition and vaccine developers are incredibly careful. They try to check every box. They try to think about every possible eventuality where there could be some risk to the population. That is by definition how we are essentially, taught to be vaccine developers. What I think is a little confusing, though, is how we went from vaccine timelines that would take 20 years down to 1 year. And that's where folks get a little confused. Did we cut corners? And the answer is we didn't. It's just that we went from our classical vaccine development pipeline, where we would essentially design our protein, and then take a look at it on the bench, and then think about it a little bit. Then we would package it up and put it into a mouse, and we would study it, and we would look at the data in and out. We'd think, is that looking as good as it could possibly be? And then we would move it into monkeys and see, did it really provide protection, and what kind of flavors of immunity? And then we would move into phase 1. And we would look at the data again. It's this methodical, slow process of potentially overly looking at the data that slow down the whole process. What happened during COVID is that we did not have the opportunity to take that slow, methodical process. But what we did is we looked at that process carefully, and we began to make efficiencies in the development pipeline, where now instead of looking at the data and thinking about it 50 different ways, what we began to do is to bring scientists from all over the world together to look at the data simultaneously. We began to poke and prod at it at that very second the data was produced. And we began to move the pipeline along at this novel speed, where we still looked at every single possible question about safety and efficacy and quality, but we contracted the whole timeline by bringing more brains to bear on the subject. I think the other really important point that I think got built into this is we began to have direct conversations with the FDA and other regulatory bodies. We no longer went along this process on our own as kind of rogue agents trying to make these vaccines in the back of our laboratories somewhere, in a university somewhere in the world. But we began to work together with the FDA and began to have that conversation about what is it going to take to convince you that we are hitting that landmark immune response? What is it going to take to convince you that we have the safety levels that are required? What do we have to test in order to really make a case that this vaccine is meeting all the criteria that are required both for protection as well as safety for any given population? And those conversations accelerated the entire process. So instead of doing it, one step at a time, slowly but surely, we just overlapped the process and started to have conversations that allowed us to capture all the same information, but interpret it in real time. And that is why we got there in 1 year. And that is why we'll never have to wait 20 years ever again to make a vaccine for any novel pathogen.
That sounds amazing. I'm very, very, I feel like pretty fortunate to live in this world where we get modern medicine where we can make vaccines like that, especially when you describe it that way. So since you talk about sort of future vaccines, I guess, coming back to the COVID-19 pandemic, you mentioned that there are other vaccines for COVID that are coming. What are they, and do they have any interesting features that aren't currently present in the Moderna and Pfizer vaccines we have right now?
Yeah, so the next one on the docket is the adenoviral vector 26 vaccine coming from Johnson & Johnson. And the emergency use authorization application in the US has already been submitted to the FDA. And so we're hoping to hear very soon of whether that vaccine will also be approved. What makes that vaccine different is that it also sends the software into the immune system to teach the system how to develop immunity to COVID-19 to it. Now, instead, it uses a common virus, and that common cold-causing virus is completely innocuous, does not cause any disease in humans, but can essentially deliver this kind of software information to cells with incredible efficiency. What makes this particular platform so attractive is really two things. The first thing is it's really easy to make huge amounts of this vaccine. These viral vectors grow in vats, and you can make millions and millions of doses really, really fast. The second thing that makes it really attractive is they are stable at room temperature, which means you can vial the vaccine and you can send it all around the world, and you can keep it in rooms so you don't have to worry about whether or not the vaccine is cold enough and still be effective, which is one of the issues we have with the Moderna and the Pfizer-BioNTech vaccines. So imagine now we'll have a vaccine that can essentially do the same thing that the mRNA vaccines do, but it can do it at a potentially in a cheaper way, as well as can be deployed globally. The other thing I just want to mention about the Ad26 vaccine is it is special because you might only need one dose to get up to 85% protection against severe disease and death. And that 85% protection is not only true for the virus that is here in North America, but also against the UK variant and the South African variants that are a little bit worrisome out there in the world. So imagine if you only need one vaccine, the globe can be immune after just one shot. And that's what makes this vaccine so attractive at a global level. The next one, oh, sorry, go ahead.
No, go ahead, please.
I was going to say the next on the docket is a protein-based vaccine. And so there is a wonderful company called Novavax that essentially makes really unique, very stable, and highly immunogenic proteins. And they are already in phase 2 and phase 3 testing. And what they do is they deliver proteins that are absolutely stable with some immune stimulants to drive really strong immune responses. Now, because it's protein, it takes a little bit longer to make these types of vaccines. But the one thing that makes this particular vaccine so interesting is in the preclinical animal studies, 2 doses of that vaccine completely knocks the virus out. There is just no virus that can escape the immune responses induced by this vaccine. So there is good reason to wait for that vaccine as well on a landscape level, because that's only going to add value, particularly with these really robust immune responses that may be desirable potentially for some populations that might be more vulnerable or may not respond quite as effectively to the mRNAs and to the viral vectors.
Right. Although I guess it's worth mentioning that if you get the opportunity to get a vaccine today, don't wait for the other ones to come out.
That's right.
Yeah. Okay, so I have some audience questions that I'd love to ask you. One of them is, once you get the COVID-19 vaccine, as I understand it, you can still get the virus, but it won't be as severe. Or I guess you could still get the illness, but it won't be as severe. Is that correct?
Yeah, so what the data shows is that with many of these vaccines, there is still the possibility that individuals can develop mild disease. And so what that means is you might have a sore throat, a headache, or some potential coughing. But what is important about all these vaccines is that they limit severe disease, meaning they reduce the need to be hospitalized. That is essentially the number one clinical endpoint that we were seeking with these vaccines, right? Is that if we could turn this disease into a common cold, I think we're going to do okay. We're going to help people come out of their homes. We're going to help people start to interact again. And that is really the ultimate pursuit that we have with this vaccine. It is possible, right, that in the future, as we learn more about this virus, that we'll completely eradicate it like we did with smallpox, as we heard about before. But that's a bigger ask, and we need to truly have the time to understand how the immune system can completely block this virus. I think we're going to make headway in the next few years to figure that out. But if we can convert it into a cold-causing virus, I think we're going to be in good shape to return to some level of normal in our behaviors in society.
Yeah, I mean, speaking of, I guess, returning to normal at some level, there's another audience question that relates to that. After you've been fully vaccinated, can you gather with other people who have been fully vaccinated or even people who haven't been fully vaccinated yet? What are the risks associated with that? And, is it, you know, I guess, is it safe and maybe even allowable?
So that's a tough one, right? Because
Yeah.
I also want to hang out with my friends and I want to hang out with my family and I want my kids to have a chance to play with their friends. It's a real hard one because I think that the problem right now is not that, let's put it this way. We know the vaccine will not necessarily prevent you from being infected, at least in the upper respiratory tract with the virus, right? So that can cause those cold causing symptoms. We know the vaccines are preventing this severe disease, but that means that even as a vaccinee, you can be a carrier, which means that even if you're interacting with another vaccinated individual, you can theoretically still spread the virus from you to that other vaccinated individual, and that person becomes a carrier. Now, when that person then goes and interacts with someone who has not been vaccinated, they are now a transmitter, and they can give that virus to other people. So the way that I think about it, I think that we're still trying to hit herd immunity. Our goal as a society should be to try to empower the entire community with a level of protection that will make sure that those that are most vulnerable or those that cannot access vaccines right now are still protected. We still don't know who will go on and develop severe disease. So as long as we have the risk that anybody, even 2 or 3 degrees away from that core group that we're interacting with, may still be vulnerable, we have to protect all the individuals who are not getting the vaccine. So what I would say is that social distancing and masks are not going to go away anytime soon. Even with the vaccine, we have to still be careful because until enough of the population is immunized, there is still always the risk of transmission events occurring from vaccinee to vaccinee that can then eventually leap into somebody who is not vaccinated. The estimates now are somewhere around 70 to 75% of the population has to be vaccinated to reach herd immunity, but those numbers are changing. And we're starting to learn really what level of vaccine coverage we're going to need to be able to have those kinds of congregations. So I would say, let's just wait for spring and maybe see small groups of individuals outside with masks and social distancing.
Yeah. I mean, I guess the vaccine, if it might protect you, it might protect other people who are vaccinated. But part of this has always been thinking about others, like sort of looking out for the most vulnerable members of our society. And I guess that doesn't change even if you've been vaccinated.
It doesn't, so I always tell people the reason you get a vaccine is not just to protect yourself. It really is to protect all those individuals around you. And the only way we reach that level of community level protection is when sufficient numbers of individuals are vaccinated. So part of our responsibility as a society is to continue to spread the word about how cool vaccines are, how protective they are, how all this data that the anti-vaxxers are putting out there is really been debunked with scientific hard data. And to really encourage people, like you said, is if you're offered a vaccine, feel safe, feel good about it, learn about it, read the right sources of information, because we have done everything we can to understand and turn that vaccine in every single possible direction to try to understand how safe and effective they really are. So we are just really fortunate when we are offered those vaccines, and we should help to get the word out there so more people can take it so we can finally get out of this pandemic.
Yeah. No, I guess on that topic, there are a couple of other audience questions that have to do with safety. And I think that these are well, I'd love to hear what you have to say about them, because I know that the trials didn't include huge numbers, or I'm not sure if they included anyone who were currently pregnant or had certain, I guess, immunocompromising diseases. So do we have any more information on how these vaccines interact with pregnancies, how they interact with people who have maybe chronic conditions like Parkinson's disease or are HIV positive?
Yeah, those are really good questions. So the phase 3 trials had to move incredibly quickly. And so what that meant is they had to do some population selection. And so what they did and what they were very effective in was selecting individuals within the age range, as you know, for Pfizer, BioNTech 16 to 65. And I think they actually went up over 75. And then Moderna went 18 up to the elderly population, and they had to move fast. They did try to cover diversity from ethnic and racial perspective, and they did cover all the ages to try to understand what those vaccines were doing across the entire spectrum. And I think they did an enormous job in a very short timeline to get us the data that we needed to make sure that the vaccines are safe and that they are effective and that they do work the way that we need them to work. Now, what they didn't do is they were not able to go into those vulnerable populations. But since the emergency use authorization, many of these large medical societies, both here in the US and abroad, have begun to do controlled trials themselves to begin to vet and test those potential vulnerable populations. The pregnant women is a topic that's very dear to my heart. It's an area of immunology that I'm incredibly invested in. And we are doing an enormous amount of immune testing in healthcare workers that are pregnant, that are electing to take the EUA-approved vaccines because they are in that first wave of potential recipients for the vaccines. And what I can tell you so far is the vaccines are incredibly immunogenic. They are incredibly safe. And they are delivering antibodies beautifully, at least in the first cases of births to their infants. And the American Association of Obstetricians and Gynecologists really put out a very strong statement to the world saying that pregnant women do have to be on that radar because, of course, as we've seen in the literature, pregnant women tend to have more severe COVID-19 disease compared to their age-matched control. So they need to be really in the forefront of our investigation. And it's just wonderful to know that there are these, societies, these medical societies that are taking this seriously. And again, they're working with the vaccine developers and the FDA to get the data to make the case of how we can move vaccines forward faster for that population. The other vulnerable populations, again, is the same story where these medical societies have come together to begin to work with vaccine developers to begin to test these products in populations that have autoimmune diseases such as Parkinson's, as you mentioned, but also multiple sclerosis, lupus, rheumatoid arthritis, and many other diseases. And there we're starting to see the data come out, and there is a large effort by the NIH under an effort called the SeroNet, which aims to specifically identify whether or not vaccines work as effectively in these autoimmune populations as they do in healthy individuals, but more importantly, if maybe some platforms might be more advantageous in individuals that have some immune potential deficits. And the same thing is being done in cancer patients, patients with HIV, as well as patients with other immunological disorders, all really being driven by the experts that have been empowered to help to drive this conversation with vaccine developers and the FDA. I think the big learning lesson will be is that we have to have realistic expectations in a really high throughput vaccine development pipeline of what can be done in a phase 3. And we have to work with these medical societies that take their particular patient population, really to heart, and to work with them to basically develop the protocols, the questions that will allow us to get answers to help protect those populations as effectively as possible. And I think that's the best we can expect in this, kind of overdrive or this massively accelerated process that we're learning from in real time.
Yeah. I wanted to quickly ask about something you briefly mentioned just now, that pregnant women might give antibodies to their infants if they got the vaccine. Does that mean you could pass on immunity to COVID-19 if you got the vaccine and you were pregnant?
Well, yeah, that's the whole point of the placenta. So, this is my favorite organ in the body. It's a funny thing to talk about on a radio show, but it's a really fascinating, organ that, we're connected to our babies by an umbilical cord that goes through an organ called the placenta. And the placenta shoots over oxygen, changes blood, essentially transfuses the baby all the time, gives it nutrients. But what it also does, super importantly, is it delivers antibodies and immunity to our infants. And so one of the reasons we're so excited about vaccinating pregnant women is not only will we be able to protect them from getting COVID-19, but they will then also transfer antibodies to their babies. And that means that babies are born on the first day of life full of antibodies that can fight SARS-CoV-2. But the reason this is so interesting is that in the history of vaccine development, we have never been able to study the immunology of vaccination in pregnancy because people are always terrified about vaccinating pregnant women because we're afraid that maybe they'll miscarry or they'll have some other complication. And so we always treat them, like sacrilegious, because we want to protect our pregnant women as much as possible because they're carrying the future of our society. But now, because we want to protect them and we have these very safe vaccines, we can begin to study the immunology of vaccination, which means that for future pandemics that might be, really lethal to babies or to pregnancies, we can now make informed decisions about when it's the right time to vaccinate, which platforms work the best, and how can we get the best antibodies possible in our babies so they can be completely resistant to pathogens when they come out of their moms.
That's amazing. 2 for 1. Okay, so there are a few other audience questions that we have here. One of them is, an audience question just asked, there are so many coronaviruses and not vaccines for every single one. So I assume these are non-COVID coronaviruses. So how have humans been able to avoid all these other viruses, I guess, that are all these other coronaviruses, I suppose, or perhaps I guess maybe simply other viruses that cause human disease?
Well, that's a really good question. So there is an estimate of over 200 different coronaviruses in nature, and coronaviruses have been passing into humans. They have been essentially mutating and entering the human population repeatedly over the last several decades. For many of the common coronaviruses, they do cause just a respiratory cold-like disease. They cause limiting amounts of disease in the population. And we've been lucky that we've been able to deal with them because they are not all that lethal. They just cause a little bit of irritant, but our immune system is able to catch up with them and to limit their potential ability to cause disease, partially because they might be a little bit wimpier. They're not quite as infectious, let's say, right? So they get in and they don't infect as many cells, or maybe they don't cause as much inflammation in the immune system. Or maybe part of it is also because they have not mutated enough to really bind to the receptors in a way that gives them this broad access to multiple cells on the respiratory tract. So there are reasons immunologically that they are not quite as fit or as aggressive. But what has happened, and I think it's really important to remember, is that there are 2 instances of coronaviruses entering humans that were really scary. SARS-1 entered the population back in the early 2000s, in 2002, 2003, and caused 10% mortality. I mean, that means that 1 in 10 people who got infected died. That is not what we're seeing with COVID-19, where we're seeing 1 in maybe 100 or 1 in 200 individuals that might have severe disease and pass away. That was scary. And the only reason we overcame SARS-1 is because it was not as infectious as COVID-19 or SARS-CoV-2. The second virus was even scarier. That was the Middle Eastern Respiratory Syndrome virus, MERS, that entered the population about 10 years ago. And that virus caused 30% lethality, which meant that 3 out of every 10 people died. And again, the only reason we survived that one is because it was not as infectious as SARS-CoV-2. So we got lucky with those ones because they were really bad viruses, right? Here we have a virus that's part of the same family. It's not as lethal. It doesn't cause as much disease. But importantly, it does spread so quickly that we have larger numbers of individuals that are getting infected. And so what this has taught us, the big lesson is that we knew SARS happened, we knew MERS happened, and we never really followed through and made a vaccine. And that was silly. We should have been making vaccines against those guys, and maybe we would have been prepared for SARS-CoV-2. But now with SARS-CoV-2, we're not going to rest until we have vaccines that work really well, right? We're going to go all the way, and we're going to make a vaccine that's going to work. And even more importantly, and just the nice little note of hope, is that we've even as a community begun to think about how to make vaccines that not only limit SARS-CoV-2 infection, but may also limit multiple different coronaviruses that exist in nature. So we're trying to learn where these coronaviruses are similar in their genomes, so we can learn how to drive immunity to protect against multiple coronaviruses, with the goal of one day making a universal coronavirus vaccine. So that is the ultimate goal. And I am confident that we are going to get there in the near future, at least definitely in my lifetime.
I think that many people would be very interested in seeing that vaccine. No, I know that there were a lot of people who thought the next pandemic would come from an influenza virus, and they were watching out for emerging new influenza viruses. I think Moderna even had created a vaccine against one just in case it became a pandemic. But of course, it came from the coronavirus group. I guess there's just a couple of minutes left, and maybe this is a question, another audience question that is good to end on. I've been hearing the phrase herd immunity since the pandemic began. Why do we need a vaccine to achieve herd immunity? I guess what is the alternative to getting there without a vaccine?
Right. So the idea of herd immunity really is essentially that we can protect our entire herd, right? That essentially everyone will have immunity, or will have enough immunity in our community. Enough people will have robust immune responses that will essentially keep the virus out, right? We can essentially completely block it from entering that population. So even if a couple of people in that population may not have complete immunity or not be vaccinated, as a community, we're keeping the virus out, right? Because we're limiting the possibility of transmitting within that population. And that is the concept of herd immunity. Now, you could theoretically wait until the virus passed through enough individuals. And you would have to wait until enough people built natural immune responses that could eventually give us enough of that immunity that stands that wall up to prevent the virus from getting in, right, into that population. But we don't know how long it takes to get to that very high number of individuals that need to have immunity if we wait for natural infection to occur, right? It could be a month, it could be a year. What we learned from New York when the virus was going crazy back in March is they only reached 20% herd immunity when they let the virus go crazy. And even Sweden, that never shut down and barely wore masks in the summer, only hit 25% antibody positivity in their population. So they were nowhere near the 70 to 75% levels of immunity we need in our population in order to truly create that herd immune response that will keep the virus out. What vaccines do is they accelerate, right, the time in which we can stand up antibodies in our population, right? We can essentially immunize vast numbers of individuals and essentially get those antibodies to sufficient levels where they can completely keep the virus out. So the reason we need a vaccine is to essentially get ourselves out of this pandemic as soon as possible. And that is the reason why we're really trying to think about ways that we can stand up immunity in a strategic way, initially in those that are most vulnerable, and then start to work our way through the population and give it to as many people as possible so we can eventually have that level of an immune response that will just keep the virus out.
Yeah, I mean, not to mention using a vaccine rather than natural infections means a lot fewer people would die from coronavirus. We are unfortunately, sorry, that was my cat's feeder going off. We are unfortunately out of time, but thank you so much to Dr. Galit Alter, Professor of Medicine at Harvard Medical School, for your time and insights. Thanks to Ben Brock-Johnson and Amory Sivertson of WBUR's Endless Thread podcast for that great introduction to the history of vaccines. And thanks to you, the audience, for joining us tonight. A week from today, on Tuesday, February 23rd at 6 p.m., will host the next event in the WBUR Town Hall series on the COVID vaccine. WBUR reporter Martha Biebinger will be joined by Dr. Paul Bittinger, Vice Chairman for Emergency Preparedness at Massachusetts General Hospital, to discuss the successes and challenges of vaccine distribution. And Ben and Amory of Endless Thread will be back again as well. You can register and find out more at wbur.org/CitySpace. Thanks and have a good night, everyone.